talk about, I'll put the clock on here. Here we go. Yeah, the fact that actually we often think of haptics as something that goes on in our brains. But here I will take the perspective that actually it's something that happens outside the body. It's actually something which is grounded in the physics of mechanical interactions that we entertain with the world around us. And what is really interesting to me, at least, is that often the mechanical phenomena that actually takes place when we interact with objects and things are often not quite intuitive. So that's what will be the theme here. So can I have the next slide, please? Yeah. So as was mentioned already, haptics is kind of the a forgotten field. I mean, what I'm showing here are panels of a famous tapestry that have been visited by a Parisian photographer recently, and show, you know, like the Aristotelian senses represented as the behavior of animals. With the so that's a tapestry that was originally created in the 15th century, and then you have vision and you have audition. Next slide, please. Next slide. And then you have taste, and you have olfaction, and then the last panel is touch, and that's the photographer here has really captured the really interesting aspect of touch. The lion here really enjoys being petted, and then so that's actually a recent development in the study of touch is actually the emotional aspect of it, which is was neglected for so long. And then you have also the unicorn, which is being held by the horn, and actually it really also illustrates beautifully the unique aspect to touch, which is this inherent ambiguity whether things are touched or you're touching them, which have been discussed by philosophers and thinkers for about a century now, whether touch is about yourself or about the world outside. Next slide, please. And so I'll start with a study done with David Georgiev like a couple of years ago, and then Jean-Louis Tonard, and at that time there was a realization that actually the sense of touch was capable of perceptual feats which are not at all intuitive. And then we actually thought that it was actually possible for people spontaneously without any training to tell by touch the difference between different materials that were extremely similar. And in that case, the materials were sheets of glass and sheets of plexiglass. And then we actually made sure that they were identical in terms of their shape, so they had no texture. And then, as we very often notice, is that texture is like a huge aspect of the study of touch. But here we show that actually it's not the only one, because these materials were perfectly atomically flat. We checked that with appropriate instruments. And we also, of course, control for the thermal effect. So there was two conditions. In one condition, the sheets were brought at finger temperatures, so there was no thermal exchange. and in other conditions, they were actually left at room temperature, and they were bonded to heat sinks. So the diffusivity was identical. So that was all controlled. And then as you see on the panel A here, that actually participants were actually capable of picking out of 3 samples the one that was made of plexiglass, or the one that's made of glass, which meant that they could discriminate the materials on the basis of tactile inputs only. So that's surprising, given that there was no shape, there was no thermal exchange, there was no anything at all. And so, but the point is, what is the panel D here, is that actually there was a significant correlation between the water content in the finger of the participants and their ability to tell glass from plexiglass. So that's really surprising and intriguing. You know, why is it like water makes any contribution here? Actually, rather the absence of water. Next slide, please. And so it's fairly intuitive that actually when you move your hand and you feel objects, the sliding velocity is never constant. It actually goes through a whole range of all possible velocities, and always starts with a stuck state, essentially when the finger doesn't slip, and there is a period of partial slip, which causes actually the periphery of the contact area to progressively invade the area of contact until the full slip is developed. And then we thought actually maybe there was information in a particular task here of telling a material that was not contained, not during the slip, but actually during the transition. And next slide, please. And actually that's what normally the analysis showed, actually, is that the particular it's like a complicated stick slip event, which takes place when the finger ceases to be in static contact with a surface and then starts moving. There's like a coarse analysis tend to show actually that actually there was more information during this 300 millisecond period, when the contact is transitioning from a stuck state to a slipping state. So that's interesting, and but it remains to be explained. So next slide, please. So what you are seeing here is nothing, actually, is actually a very high resolution image of the quote-unquote true contact area between the finger and smooth and non-permeable surface, smooth, hard, and non-permeable surface, which is glass, okay, and plexiglass too. So these are 3 physical properties that are fundamental to touch: the fact they are smooth, that there is no water exchanged, and that actually they are the hardness is bigger than the one of the finger. And then so the surprising fact here is actually the contact area is almost invisible. Next slide. Next slide, please. Next slide. Next slide. Next slide. Next slide. So really what the point is here is that actually an interesting phenomenon is taking place when you actually touch a hard, non-permeable, and smooth surface. All these 3 properties are needed for this phenomenon to take place.
And then that's something that is explained by my colleague Mike Adams, who is a chemist at University of Birmingham, who has studied actually contact mechanics and the physiochemistry of contacts for a very long time, and in particular when it comes to skin. As you all know, skin is covered. All skins actually across nature are covered by a layer of keratin, which is it's a natural polymer, and the keratin, which is almost the same material as your hair and nails, but the one on the skin is a little different. It's keratinized cells, which once stabilized can undergo a phase transition when they are above a certain level of water contact. And what the phase transition does is actually modify their the Young modulus, or mechanical property of the keratin, not by a small amount, but by a factor 1,000. So basically, the keratin can is very, very hard when it's dry, and it becomes very, very, very soft when it's wet, and everything in between. So what seems to be going on here over a time scale of about 10 to 20 seconds is that the water exuded by the body gets trapped against the hard surface and smooth surface, which is represented here by glass or plexiglass, or it could be ceramic or metals. And then the water content undergoes a first order dynamics. So you have a diffusion process, which causes the keratin to change transition, and then over a period of 20 seconds, increase the contact area by a huge amount. So this is very interesting and intriguing. So it has two consequences. The one which is motor control. So for example, if you hold a glass of beer or wine or whatever, something which is not permeable, then essentially the motor effort to keep it not slipping ceases after a few seconds to be necessary. So essentially you have this really very high friction after, simply by waiting for during the contact. So that's one interesting consequence. That would not happen with paper, for example, because the paper would diffuse the water, and then it would actually become more slippery by waiting, and then you have everything in between. That's possible. This phenomenon also depends on the roughness, but I'm talking here about roughness at a small scale, not the roughness that we normally think about, but roughness which is micrometric, and of course depends on the fact that on the ambient conditions, whether there is water in the room or not, or the climate, etc. So this is really incredible, because we never realize that normally, that you probably never realize that when you're holding paper or a piece of metal or something that is porous, that there are such incredible variations of the coefficient of friction. And I'm talking about not about a factor 2, I'm talking about orders of magnitude. So this is a miracle that actually our motor system can account for that in order to secure good grips and very completely automatically. And also, I believe it's really one of the fundamental phenomena that makes us discriminate the particular materials that we touch, whether it's wood or stone, and all these different type of materials will create water diffusion dynamics that eventually translate into sliding dynamics that are picked up by the brain and used as an identifier for the material that you use, that you are touching. Next slide, please.
So here's another non-intuitive mechanics that I was very intrigued. I think I already spent my time, so I will. I think we had only 20 minutes, and I started at 10. So what I'll go very quickly and conclude. Here, what we realized actually with Alessandro Fane, and the study was conducted mostly by Luke Miller, who is now a young professor in the Netherlands. Essentially, what we realized that actually people could tell spontaneously at when they held a piece of wood, and actually I have it here. So that's essentially the instrument you use, piece of wood here, and then when you hit with an object with the wood, or an object comes and hits the wood here, then you can spontaneously tell exactly, very precisely at the location where the contact took place, and that's really not intuitive. Normally, you would follow one of the earlier hypotheses about tools, and they are shown on the panel here on the top left. The tradition from David Katz, like a century ago, essentially that tools let you distalize sensation. So essentially, you have a contact at the tip of the tool, and then by some process, the brain takes the tool as a extension of your own body, and then you can actually feel the tip of the, say, the stylus or the pen, or the example that Kat used, the tip of the needle. When you're sewing, then you don't feel the fabric with your finger, you feel the fabric with the needle. So that's one hypothesis. In the mid of the 20th century, there was another sort of cognitive hypothesis that actually the sensation inside the hand were somehow projected at the tip of the tool. So that's another way to look at it. And then what we thought that actually is that there was a third possibility, which actually tools are quote unquote embodied by our brain. Basically, the tool is not different from your hand. And so since I have spent all my time, well, I'll stop here, but essentially we've collected a lot of behavioral evidence for that, and also very strong neural correlates that show that actually the brain dynamics involved in using tools are extremely similar to the brain dynamics involved in using your own limbs. And so with that, I will stop and take a few questions.
So thank you very much, Vincent. Is there any question here? If there is a question,